I would say an ideal digital twin is a living, breathing digital replica of a real-world process or facility. If there isn't some component of real-time data, then it's just a great model. Reality capture is going to be a foundation to getting to that ideal digital twin model.
As pioneers of this technology, we need to share our knowledge. Our collective societal growth rests upon leveraging these technological advancements.
What do we need to do with this reality capture data to get it into systems and processes that we use to make decisions?
When we get called to action, it's often because processes are broken or infrastructure is faulty.
So standardization of these is really critical to have functional data from reality capture. We can aggregate multiple different types of reality capture data into a single data set for visualization. One of the important things about a utility is there are lots of different end users and organizations, but each one of these parts of the organization has information the other ones can use. So they have to go look and dig and find. If you don't know the right person, you may not find access to that data. So building functional integrations with these systems puts that data from one organizational construct into another so it can be leveraged for better decision-making, better analytics. Really, reality capture becomes that foundation of digital twin to know that what we're looking at in our digital twins are the existing conditions, that they're functional. And ultimately, we can make better decisions, do better designs, perform better analytics, and improve all of our processes because we know what we're working with from the very beginning. Thank you very much. I'm glad to be here for the Reality Capture Network Conference. I'd like to thank Matthew Bird for inviting us out here. Matthew Ard is speaking with me today. We're from Power Engineers. We're a fairly large engineering company. We have a broad industry. We cover a lot of different industries, but one of our main focuses is the electric utility industry. So the focus of our talk today is going to be on electric utilities and how reality capture is leveraged in those industries. There's some subtle differences between them that we'll talk about as we get into this as well. My name's Aaron Mason. I'm a senior consultant for Power. My focus is on digital twin, intelligent design, and reality capture. I'm originally from Anchorage, Alaska. I've worked in civil construction and utilities for about 20 years, from survey to inspection and testing for dirt work and concrete and foundations to drafting and to CAD work and to GIS management. So a broad range of different experiences really helped inform the way I look at reality capture for utilities.
My name is Matthew Ard. I hail from Green Bay, Wisconsin. I've been in the CAD and engineering design industry for about 16 years. I've been with Power for a little under a year. I'm going to be talking to you today about vault scanning, particularly underground vault scanning in electrical environments. That's about it for me.
All right. Thanks, Matt. So first off, why reality capture for utilities? We're going to highlight some of the differences between the AEC industry and utilities and how reality capture might play a little different role for them. Reality capture for utilities, speaking for electric utilities, but it covers also similarities with gas and comm, sewer, and water. Generation facilities can be large industrial plants, power generation, water reservoirs, dams, those types of things. Transmission lines are more similar to large civil projects, so large highways or pipelines, that type of infrastructure. Substations are more like small generating facilities or small distribution facilities, gas regulating stations and those type of things. And then distribution is what gets into your home. You know, your gas lines to your home, electric lines to your homes. So there's really a broad range of different applications and projects that are covered by utilities. So it covers a wide range of industry uses. And also utilities have the owner-operator side that we're going to talk about as well. The way we look at reality capture for utilities is looking at a lot of different tools for lots of different applications, from terrestrial scanners to mobile and SLAM solutions to drone solutions to a diverse range of other sensors that we can use. The way we look at it is because there's a broad range of different uses for utilities, we're looking for the right tool or combination of tools to meet those business needs. And those business needs have a wide range from inspections to regulations to asset management to construction and operations. So we're really looking at a broad range of tools. We'll talk a little more specifically about some of those tool sets as we get into this. Also, I speak quickly. If I go too fast, someone raise their hand. I'll try to go slow. We're talking about the foundation for digital twin as well. Digital twin can be a different term for a lot of different people. The way we're defining digital twin, and I would say an ideal digital twin, is a real-world, living, breathing replica, digital replica of a real-world process or facility. Right? And there can be many components to that. There can be many evolutions to get to that ideal digital twin. And I think most of us have some components, but the ideal digital twin of something that represents the real world as it is today is really the golden standard we're looking to. I think lots of things that we've talked about today are moving towards that process, but not entirely there. Sean Weekly, who's one of our digital transformation experts at Power, said, if there isn't some component of real-time data, then it's just a great model. I think that's a great way to think of where digital twins should be going. Does it represent the real world as it is and the processes that are happening in real time, and how do we get there? So we'll cover on why reality capture is going to be a foundation to getting to that ideal digital twin model. We're going to cover data capture, so 5 pillars to what we're talking about today, collecting the data that we need for a digital twin. We'll talk a little bit about data processing, how we create our digital twin, taking that collected data and converting it into things that we use to actually build that digital twin. Data management, how we organize and get the components structured so our digital twin can be functional. Data integrations, all the diverse systems and places that the data lands and goes, and how we bring those systems together so that they can operate within an ecosystem that supports each other, so that data that's in disparate systems can be leveraged for additional analysis or additional functionality for whoever the end user is. And in utilities, there's a diverse range of systems that we'll talk about how important that is as part of this. And then data sharing and analytics, really using our digital twin. Once we have the data stewarded in a way that we want, once we have it integrated and have the data consolidated for the end users, how do we share that with the end users? How do we use compound analytics? How do we get more out of our digital twins? What are we trying to use that data for? So the end users can make decisions, improve their processes, do a better job, and be able to have better information at their fingertips than they had before. If we're not providing some real end use cases with the digital twin, it's not really meeting our business purposes. So we look at what business problems are we trying to solve with digital twin, and how do we get that into the hands of the end user. Right. So we're going to start with data capture, and we have a use case that Matthew Ard is going to highlight for us on underground vault scanning, and after he's done, I'll get into some details, some other data capture elements. Matthew.
Thank you very much. I'm going to rely a little bit on my phone for notes because our notes aren't up here, but it's kind of like having a backup to the backup, which I'll kind of touch on as we get into this data capture use case. So I'm going to address a unique challenge today, capturing the condition of an underground electrical vault, which we were not able to access due to major safety concerns, notably the rapid water filling of the vault. And so we needed to devise a safe method to capture its internal state without putting anyone at risk. So the process for scanning an underground vault is extremely tricky. And we had to come up with a way, given the circumstances of the project, we needed to get a little creative. We understood the reason we were being asked to perform this scan was to help provide solutions for eliminating water penetration. The best way to do that would be to georeference the scans, which would allow further analysis, taking elevation and proximity to other utilities and infrastructure into account. So we needed to understand the task at hand, and for this project, it wasn't an option to enter the manhole, and so we decided we needed to get creative and we had to invert our RTC 360 to lower it down into the manhole to get the scans. So this helped us avoid some substantial risks and get the job done a lot safer. Some important questions that we needed to consider. There was a lot of challenges. So we started to compile like a list. We talked to all the safety personnel that we could within Power, with the client. We had sit-downs with each other. And we started compiling this list of obstacles that we knew we needed to overcome. How do we capture the data safely? You can read some of that yourself, but we needed to, geolocation was probably the hardest thing to overcome, and making sure that we had adequate lighting down inside the vault so that when the scanner took a panoramic photo, it was capturing the colorized scan data. And then keeping the water at a low enough level because it was filling so rapidly so that we didn't, hurt the equipment. So we began to ponder these questions, and it helped us come up with solutions that we knew we needed to overcome. So geolocation was sort of a new thing for us, and after a lot of researching and brainstorming, we figured out how to accurately geolocate just about anything. And here's how we did it. So we would essentially set up points above ground and locate those points using georeferencing tools, and then scan above ground, and then we would invert the scanner immediately and locate it above the manhole. And we had some, you may not see it on this slide, it's probably on the next slide, but there was a sort of a creative way that we put together some spherical targets and mounted them to a tripod, lowered those into the manhole, and then we were able to capture data above ground and below ground, and then immediately lower the scanner below ground and scan again, and that allowed us to ensure that the scans were oriented and georeferenced properly. So there was some worry about the viz system. If anyone's in tune with Leica, sometimes the viz system on the RTC 360 can be a little bit unreliable. In this case, it ended up working. So that was a big hint for us, or big help for us. But we needed this backup plan because, the client was spending good money for us to be there, and we wanted to ensure that we could get the job done and not have to go back. So you can kind of see there, we've got the tripod with the spherical targets down in the manhole. And, this kind of same thing you guys have probably heard more of, a video's worth 1,000 pictures. So for this project, we also utilized a FLIR 1 Edge Pro. It's a thermal imaging camera. We were able to lower that down into the hole and essentially just rotate it around, stop at some critical pieces and collect temperature data on some of the hottest points inside the hole. And then we also used a Theta X 360-degree video camera, which we also just, put on the end of a prism pole and ran it down into the hole, and we didn't even have to rotate that one because it takes a 360-degree video, and that was it, worth a lot of in terms of what we needed to get for the client to further analyze and help them figure out what to do next. So where are we at? So you can see there the FLIR 1 Edge is taped to the end of the prism pole, and the Theta X there is sitting next to it. Those are the two tools that we used. So the vault was filling with water at an alarming rate, and we needed to understand exactly where the water was entering, and we were able to provide this information to the client, which could then be used to analyze what was happening and consider a more reliable path forward. And here's some real video of what we captured that day. So there's a high number of safety risks and process-related challenges to consider when performing underground scanning. In this case, we didn't need to enter the vault, luckily, but in a lot of cases and in some previous projects, we needed to enter a lot of vaults. And so you got to consider what you need to do to make sure you maintain safety during those times. So we had conversations with veteran electrical engineers, conversations with each other. We needed to ensure, if you're going into a confined space, there has to be gas monitoring. So these are some things for you to think about if you're going to get into this space. You're dealing with high voltages, potentially. Electrically certified personnel need to be on site for that. Effective traffic control measures are vital for especially a rural setting. And everybody needs to wear the proper PPE, reflective vests and things like that. Sometimes you get variable depths of the vault, so you have to do assessments for each vault. And the presence of water, obviously in this case, was there, but also raw sewage was also a hazard in this case. There was some structural integrity issues to consider. You're lowering ladders down into a slippery, wet floor, things like that to consider. Intense summer heat becomes a factor, and so you want to take that into consideration when considering your timing. High traffic volumes, rush hour. Proper lighting, we talked about that a little bit. That's process related, but it's also safety related. You got to be able to see what you're doing. Also, you need to adhere to the local standards, jurisdictional standards, and in the case of the scan you see here, we had to get the police to help control traffic, which seemed to be a specific use case because that wasn't the case on all the projects I've been on. And then using non-conductive equipment like dielectric boots, arc-rated clothing, and things like that. All important things to consider. So I went through a lot of these challenges already. You can see, high traffic volumes. That particular project was in Roslyn, New York City. And then, of course, the presence of water in the manhole, you can see there. So reflecting on our project, there were some key lessons that emerged after the fact. Need to understand the client's end goal, which allowed us to strategize effectively and help get the job done as efficiently as possible. Also, involving the contractors early allowed us to save a lot of time. In the particular case where the manhole was filling with water, we didn't realize that they needed to start pumping out the water a day in advance in order to be ready for us to come and scan the following morning. So luckily for us, we were able to work with them, and they helped us out by letting us know that. Educating. There was a lot of talk about that earlier. As pioneers of this technology, we need to share our knowledge. Our collective societal growth rests upon leveraging these technological advancements. But above all is safety. When we get called to action, it's often because processes are broken or infrastructure is faulty. And so every project is going to carry inherent risks. And our role is to navigate these with safety controls and innovative solutions. So let's always prioritize safety. And with that, I'll hand it back to Aaron. Thank you.
Thanks, Matt. Appreciate that. So we talked about Matt's use case because it highlights several different components of reality capture that we can use. So I'm going to dive into a couple other methods. So traditional things we think of for reality capture, normal photo and video, these are easily accessible, democratized, people can capture them on their phones. There's lots of high value for these. They provide value that things like LiDAR and other sensors can't. You can do things like condition assessment, broken insulators, burnt out cross arms, things like that on poles. Videos provide a different context. Like Matthew shared, the water coming into the vault, we can measure flow rate from the water that's coming into the vault. We can see where the penetration's happening, where the highlighted areas of concern are for something like that. Photos and videos have the other component of photogrammetry. Photogrammetry is a lot different. You've seen some slides now about using drones for photogrammetry. So this method, though, has a lot more technical requirements. Your photo overlap, your flight patterns, your camera resolutions, all those determine the quality of the end product you get. You may have grid patterns for orthophotography, or maybe helical patterns to do 3D modeling of towers and different structures. So photogrammetry is an important element, but it takes a higher level of technical skill than traditional photos and videos. Obviously, LiDAR data. I'm a big fan of LiDAR data. Outside of photogrammetry, it provides a lot better physical measuring and modeling. You can penetrate vegetation to get ground terrain. You have intensity values that can be used for other types of analysis or classification. So there's a lot of high value in LiDAR, can be very complementary to photogrammetry. But also, as we mentioned earlier, there's different use cases for different technologies. If you're doing vegetation management, you may want LiDAR so you can penetrate the canopy and see the ground. It may not be required if you're using orthophotography and photogrammetry for other practices. So really what you use is dependent on your use case. And then really, I want to highlight different sensors. We saw the thermal image that Matthew shared, but things like infrared, multispectral, ground penetrating radar. I've 3D modeled ground penetrating radar, put it into Civil 3D to identify underground facilities and reference that to civil designs. Things like electromagnetic locating, SF6 gas detection, methane detection. All these are other types of sensors and packages that can contribute to this reality capture model we're using to build these digital twins. And they can provide insights that we can't see with the naked eye, provide us valuable data that can be integrated with other types of data so we can see a broader picture of what we're looking at for our digital twins. The key component after this collection is our data processing. This is how we create our digital twin. There's a lot of different softwares out there. You'll see some vendors. Really navigating the software landscape can be challenging, but some of the key components are what our outputs need to be. What do we need to do with this reality capture data to get it into systems and processes that we use to make decisions, to do engineering design, to do analysis, to perform asset management, and those types of things. And there's a broad range of different softwares that do that. Those outputs can be defined depending on their purpose. it's important for us to understand the business case, so we define our outputs to correlate with our capture methods as well. This could be mesh models for certain different types of analysis, point clouds, FBX files, DWG files, any range of outputs, but defining those outputs and how they're going to fit into our ecosystem of products is important for us in the processing. We should be standardizing our processing methods to get the outputs we need with the data that we need in order to support our business processes. So standardization of these is really critical to have functional data from reality capture. One of the key components that I've used before is just digitization of this data, right? Converting that point cloud or that orthophoto into a DWG file. The utility I worked at previously, we implemented drones for surveying, generating our topographic maps. Prior to using them, our traditional survey process with GPS and total station, we spent about $4,800 an acre to capture sites. After implementing drones, we cut that cost down to $1,100 an acre, a 78% cost reduction overall for our surveying with better end products. More comprehensive coverage areas, ortho photos that we could reference, larger site areas were captured because we could cover more area in a shorter amount of time. So some really great deliverables, and the end product was this digitization that we used to replace existing processes. And sometimes there's a step process to getting to the end product we want. I talked about the ideal digital twin. There's a lot of intermediate steps we can go through. We can realize value without getting to the ideal end process, but we can move incrementally towards that end goal. Then feature classification and generation. There's lots of AI, machine learning models, photo vision, those types of things that are enabling more automation of the functional use of point clouds. So automated classification, Trimble released, I think this last month, their AI model for mobile LiDAR, that if you look at the comparisons to their previous feature classification models, it's a lot cleaner, a lot better. Those things are advancing at a rapid pace. So looking at feature classification and feature generation are some key components of streamlining workflow and to getting usable data into people's hands. This comes to our data management portion. So once we have processed our data, we have it in usable formats. What do we do with that data? Where does it live? Where does it go? Where are we storing it? How do users have access to it? So you need to find a robust data management plan. This can be network file shares, cloud services. With the data we're talking about, reality capture, some of the challenges are large data sets. 50 miles of mobile LiDAR data is 1.5 terabytes. That can be a single project, right? Which is orders of magnitude larger than your typical DWG files or other outputs you're receiving. How are you going to manage that data? What's your organization going to do to utilize that? If this lives on someone's desktop, it loses value immediately because people don't have access and those outputs aren't readily available to other end users, right? This comes to one of the key components for utilities I want to talk about is the infrastructure lifecycle. So the way that we look at reality capture is an asset, just like a physical facility you build. Utilities are owners, operators, and builders. That owner-operator portion is really where utilities have a lot of value, and they already have existing systems in place to manage that data. Where AEC and utilities differ, AEC tends to be more innovative. They've adapted some of these practices and processes of reality capture and BIM and automation because they have to be competitive in those markets. Utilities are maintaining 50, 100 years of data for existing assets. And lots of times their design processes are tailored to fit into those systems and may not be as intelligent or as advanced or as innovative because they have to be tailored to existing processes. So this life cycle is how an asset lives. We want to talk about from cradle to grave what happens to those facilities. What happens at each stage of this process? Who manages the data? Who's responsible for it? How does it move to the next stage? How do we reinforce processes and workflows that capture what the last person did, move it to the next stage with all of that data intact so that it can be usable? And when it makes the entire round trip, the next person who touches that asset, they have all the information that was captured over the life cycle of that asset. Reality capture can play a key role in that, but it has to be incorporated into workflows. And how we store and manage that data really is how we keep that accessible and functional for this life cycle. A quick example, there was a transformer that we built. This was a small distribution project, and there was controls in place and workflows for review of this process, where on the print, the orientation of one of these electric transformers was shown one way. In the notes, it was specified another way. When it was installed facing this block wall that you see on here. So they had to rotate that transformer, come back and change it. It was a small change, but the review process missed it. The construction missed it, and so at each stage in the process, something was missed to send someone out back for that work. When the crew went out the second time to rotate that transformer, it was a simple job. They picked up the pad and rotated it. But as they were reconnecting that transformer, a lineman got electrocuted. If he didn't have to go back, he wouldn't have been life-flighted to Seattle. He would have spent 2 weeks in an ICU. He wouldn't have had to go through all this pain and problems, and there wouldn't be all these other safety issues that rose just because somebody missed something on a print, right? The reason I highlight this is not necessarily for reality capture, but that infrastructure lifecycle, if our processes and workflows reinforce data and quality and accuracy, we can save a lot of time and money and energy, and we can save costs and these safety issues you might have by somebody getting injured or hurt on the job. Data quality and organization is also key to this data management. What requirements do we have to capture it? Matthew talked about geolocating that vault. For just that vault model itself, geolocation isn't a priority. But for that utility to know physically where that asset is in relation to the entire network and system they work in, that is important. So we have requirements for when we capture data: survey control, geolocation, temperature, time of day, point quality, point density, accuracy of those scans. All those components allow us to take this data and steward it through that life cycle so it's usable to the next person. We can aggregate multiple different types of reality capture data into a single data set for visualization. And we can look at different timelines for capture. We can associate that to projects and dates and times and know when it was captured, what it was captured for, and then leverage that for future processes. So 5, 10 years down the road, when the next person has to interact with that asset, they have all that existing information right at their fingertips to use. That's how important data management is to enable those processes. If we're managing data well, the next step is integrations with data. And there's been some talk about different integrations as well. One of the important things about a utility is there are lots of different end users and organizations. You have asset management software, outage management software, GIS systems, financial groups, operations groups, regulatory groups, dispatch. So you have all these different components to an organization. They have their own workflow, their own process, their own software, and their own systems. But each one of these parts of the organization has information the other ones can use. Lots of times at utilities, one of the challenges is finding that information and that data. So they have to go look and dig and find. If you don't know the right person, you may not find access to that data. So building functional integrations with these systems puts that data from one organizational construct into another so it can be leveraged for better decision making, better analytics. Harvard Business did a study on asset management. And there's another study done by, I think, Kansas DOT. They interviewed a few DOTs. For every dollar spent in pre-construction and design, you save $4 to $10 in operation and construction costs, right? And so that means better investigation, better existing information, better design quality, eliminating change orders, return to the site visits, the things that we've talked about before. But for utilities, for every dollar spent in pre-construction and design, you save up to 100 times that in asset management over the life cycle of that asset. So for something you're maintaining for 30 to 50 years, you're recouping that cost every time someone needs to know something about that asset. If you include reality capture in that, that magnifies that information. But an important component to that is it's hard to realize that benefit if people in your organization do not have access to that data in the way that they need. We've seen this, the different systems involved. I'm gonna move through this quickly. These are lots of different systems that are involved in this building information model. Smart streetlights, smart meters, as-built records, outage management systems. Utilities do a lot of system modeling for electric systems and analysis and those types of things. So all these different systems or components we're trying to integrate and bring data from other sources so that we're all using the same information and not recreating it or duplicating it or have to go gather that information a second time. Data sharing and analytics, this is really where you get the value out of your digital twin. You have to build this foundation from the ground up. If you don't capture and collect the data correctly, you're not gonna have the information you need. If you don't process it into usable formats, it's not gonna be able to support the end users. If it's not managed, people don't have access to it and can't get what they need out of it. If it's not integrated with their systems, it may not be available to them in the systems they need and the places they wanna utilize it to make decisions. And then if we don't share it and use it for analytics, we're really missing a lot of the value. So this is a video, it's a vault model we talked about. The end value is when we do use reality capture, we can have real-time information. The workflows and processes need to support that we know what's existing at any given time. We've used vault scans for inspection. We captured them for design and for asset management. But inspectors who needed to verify asbestos fire tape could look at our vault models and identify the absence or presence of asbestos fire tape without road closures, without entering confined space, without entering a high voltage situation. We can model the existing utilities around those to do engineering design and analysis. So if we have this integrated into our system and our workflows and processes support good quality data and data stewardship, really reality capture becomes that foundation of digital twin to know that what we're looking at in our digital twins are the existing conditions, that they're functional. And ultimately, we can make better decisions, do better designs, perform better analytics, and improve all of our processes because we know what we're working with from the very beginning. Thank you for your time. These are our LinkedIn profiles. We really appreciate everybody being here, appreciate the time we have here. If you have questions, please, we'll be around for the rest of the conference. And thank you very much.
Thank you.